session, right. So, in the previous lecture we were discussing about the basics of conditionally stable system with the help of Routh-Hurwitz criteria, and then we discuss about the drawback of Routh-Hurwitz criteria, that it will not able to explain about relative stability. So, to explain the relative stability we are going for root locus. So, we would like to see the root locus in detail today. So, today we will see the basic example of root locus. We would like to determine the value of k from graphical method. Then we would like to see the concept of dominant pole. We would like to see the importance of root locus and construction of root locus. Okay. So, last time we were observing that system k over s s plus 2. So, whenever I am converting the system in closed loop, I have to apply a feedback, okay. And after that, if we calculate the quadratic equation via this formula, then we are getting s square plus 2 s plus k. So, in the root locus, what we are doing, we are varying the value of k from 0 to infinity. So, now we would like to see what is happening if I vary the value of k in this equation. So, last time when I told you, when I put here k equal to 0, then my question will become like this, and the two roots are coming here, one at the origin, second at minus 2. Now, when I increase here the value of k from 0 to 1 by 2, okay, then I increase the value of k 1 by 2 to 1. Okay. Now, see then what will happen. So, whenever I make the value k equal to 1 by 2, so my roots are coming minus 1.7 and minus 0.29. So, previous case when my k was equal to 0, right, and now in this case when I put k equal to 1 by 2, I am increasing the value of k. So, my pole is shifting towards minus 1.707. In the same way, here my pole at the origin, it is shifting towards the point minus 0.293. Now, further I increase the value of k to the 1, my values are coming what, 2 equal roots at minus 1. So, whenever my k was equal to 0, this was the location of pole. Now, I increase the value of k to 1, so it is shifting towards minus 1. In the same way, from this origin, this pole is moving towards minus 1, and now they are overlapping with each other, right. So, repeating roots are coming here at minus 1. Now, further if I change the value of k from 1 to 2, further I am increasing value of k. So, what is happening? This is the location of poles. So, initially I was at 2 and this pole was 0. So, when you increase the value of k, they are coming towards minus 1, this origin pole also coming towards minus 1, and one pole is moving towards minus 1 plus j, second pole is moving towards minus 1 minus j, and then these poles are here, right. So, in this way you can observe, if I change the value of k, then roots of this equation also varying, or you can say location of poles is also changing, right. So, basically this path is known as root locus, right. So, here you clear what is the meaning of root locus. So, this is the basic example where we are varying the value of k from 0 to 2. Whenever I vary this k from 0 to infinity, then I will obtain a certain path or locus, that will be the root locus. Okay. So, we will see. So, one condition is here, that is the angle and magnitude condition. If we want to know any poles or any root, whether it is lying on the root locus or not, whether it is lying on the path of my root locus. So, I have to check the angle condition and magnitude condition. Okay. So, here I need to write the quadratic equation. So, further I can solve it, GSH is equal to minus 1 plus j 0. So, here if I calculate the mod of GSHS, so it is equal to 1. So, this is known as basically a magnitude condition, right. Whenever certain roots lying on the root locus, so it always satisfies the magnitude condition, it means its mod will be always equal to 1. Okay. And second is angle condition. So, if I determine here the angle GSHS for generalized case, for minus 1 it is 180, or you can say whenever I am having the n number of generalized term, then it will be 2q plus 1. So, this 2q plus 1 tells you odd multiple of 180. okay, odd multiple of 180. It is written here. So, angle condition is what? Whatever poles lying on the root locus, if I determine the angle and angle if is coming odd multiple of 180, then I can say that particular pole is part of root locus. Okay. This is the thing, and the angle condition you should determine whether any pole or root lie on the root locus, and root locus will satisfy every root of quadratic equation for different value of k. Okay. So, we will see this thing. Okay. So, before going to further explore about the angle condition, we should know how to calculate the phase and angle of this complex number. Suppose a plus j b and a minus j b minus a plus j b minus a minus j b is given, their magnitude would be same. The difference will come whenever you are going to calculate their phase. So, a plus j b phase would be tan inverse b over a, tan inverse of imaginary part over real part, right. So, this is the way that we calculate the phase. Whenever it is a minus j b, so we can write directly minus tan inverse of b over a. So, if you see them on the S plane, you can say sigma is here, right, and sorry, sigma is here and imaginary part is here. Okay. And here if you plot a minus j b, so this is my a minus j b, you can assume here it is a, this is b. So, this is minus j b, right. So, if I calculate the phase, so phase would be what here minus. So, whenever we are moving from this 0 axis to the anti-clockwise, so basically it will give us a negative. So, when we move in the anti-clockwise, we will get the negative phase, and when we move in the whenever we move in clockwise, not anti-clockwise, when we move in clockwise, we will get negative phase. When we move in anti-clockwise, we will get here positive phase. So, this concept we will discuss in unit 5 in detail. Okay. So, this is happening here whenever I am writing a minus j b, this will gives me negative phase. Now, next is minus a plus j b. So, when I see minus a plus j b, so minus a will come here and plus j b is here, it means it will be lying here. Suppose b is coming here. So, this is minus a plus j b, right, and what I am doing, I am moving in the, you can say, clockwise rotation. So, what would be this angle? So, this angle basically you can calculate, you have to measure from here because you are moving in the anti-clockwise direction. So, this angle can be written as 180 minus of tan inverse b by a, right. So, this angle will be 180 minus tan inverse of b by a. So, this concept will help when we calculate the magnitude and angle condition. The same way, whenever minus a and minus j b is here, then this angle will become 180 plus tan inverse b over a. Okay. So, on the basis of that, we would like to solve one more numerical. So, here unity feedback control system is given, it means H s is equal to 1, has an open loop transfer function G s equal to this much, the gain k for which s equal to minus 1 plus j will lie on the root locus of the system. Okay. So, here we would like to know what would be value of k, and it is given this s is lying on the root locus. If this s is lying on the root locus, so it will fully satisfies the quadratic equation and it will satisfies the angle and magnitude condition. Okay. So, what I would like to do, I need to solve this example. So, here you can say it is k over s square plus 7 s plus 12. So, I need to calculate it mod, and we need to apply the magnitude condition is equal to 1 for this value of pole, that is s equal to minus 1 plus j. So, I will put s equal to in this s equal to minus 1 plus j in this expression, and then I would like to know what would be the value of k here. So, if I solve it, so k upon s is minus 1 plus j. Okay, and you can say this s will replace by 8, so it is minus 1 plus j whole square plus 7 multiplied by minus 1 plus j plus 12. Okay, this will come. Now, if I further solve it, this expression in the denominator, minus 1 plus j will come here. Okay, and if I open this formula, it will become minus 1, you can say square of it, plus 1 is here, then plus j square minus 1, then minus of 2j, it will multiplied with this bracket minus 7 and plus 7j, okay, plus 12. So, if you further solve this denominator part, it will come minus 1 plus j. If you solve it, you will get 5 plus 5j, right. You are getting this term. So, what is the expression? We can write here our new expression for you can say mod of g s at s equal to minus 1 plus j can be written as k over minus 1 plus j multiplied by 5 plus 5j, right. So, I need to calculate it mod and then I need to equate it to the 1. So, here it can be written as this is 1 and 1, it is root 2 mod value, this is 5 and 5, if you calculate the root value would be around 50, okay. And if you solve it, if you further solve it, so it will become k equal to root 100 and here my value of k is coming 10, right. So, in this way, if this root is satisfying my root locus, then the value of k is coming here 10. So, this is the solution of above problem. So, here D option would be correct option. Okay. So, this is the one numerical over magnitude condition. The alternate method is here to determine the graphical method here. So, for graphical method, we know that the closed loop transfer the transfer function given as you can say here g s, sorry, the open loop is transfer function given as g s equal to k multiplied by n s is the numerator part and d s is the denominator part, and then we are equating to the 1 for magnitude condition, right. So, if I solve it, so basically k would be written as d s over n s, right. So, this n s will give us 0 and d s will give us the pole. Basically, in graphical method, d s will represent or will give us length of pole, okay, and this n s will give us the length of 0. Okay. So, I can write this equation in terms of k length of pole upon length of 0 from this concept. Okay. So, here this is my way to determine value of k. So, this is the alternate method. So, what I will do, I would like to plot my all the poles of the system. So, if I see my transfer function in the numerical, so this is the s square plus 7s plus 12, and after solving I were getting this type of root for this value of s equal to minus 1 plus j. Okay. So, here if I solve this equation, I am getting s plus 4 s plus 3. So, I need to plot one pole at the origin, one pole at the minus 3, one pole at minus 4, right, and one complex pole that I am saying minus 1 plus j, it should lie on the root locus. So, here if it is lying in the root locus, it will satisfy the angular magnitude condition, okay. And I would like to know the value of k for this location. So, I need to know the location or distance of this pole from origin, distance of this pole from minus 3 and minus 4. So, I am saying distance is LP1, this distance is LP2 and this distance is LP3. So, how should I calculate LP1? So, I will drop here a perpendicular, basically it is minus 1, you can say this value is minus 1. So, LP1 can be calculated from here. So, this distance is 1 and you can say this distance is 1 here. So, you can easily calculate LP1 is, you can say under root of 1 square plus 1, basically it is root 2. In the same way, if you like to calculate the LP2, this distance, okay. So, here this distance is 2, this length height is 1, and if you calculate the LP2 under root of, it is 1 square plus 2 square, it will gives you root 5. In the same way, LP3, this distance is 1 to minus 4 is 3, 3 square, height is 1, it will gives you under root of 10. So, what would be value of k? It will be multiplication of all the distance LP1, LP2, LP3, that is 10. So, in this way you can calculate the value of k from graphical method. If zeros are given, then you can draw its distance from zeros also, and it will come in this formula in the division, and we will get the value of k. Okay. So, now we will like to see what is the root locus again. So, root locus will gives the stability of closed loop pole with the help of open loop pole. So, generally for root locus open loop transfer function is given. So, in the root locus we have to observe the open loop transfer function and then we need to tell the stability of closed loop system, right. So, in this case how we are observing the closed loop system by varying the value of k from 0 to infinity, right. So, it gives the range of k for which system is stable. If we draw the root locus, so we will find that for finite value of k my system is stable and for finite value of k my system is unstable. So, we will clearly obtain from root locus when we draw it. So, it will also tells you the value of k for which it is marginally stable and you will obtain the frequency of oscillation if the system is marginally stable and it will gives the relative stability. Okay. So, if root locus moves away from imaginary axis, that is LHS of S plane, then the relative stability increases. If root locus move towards the imaginary axis, then you can say towards RHS of S plane, then relative stability will decrease. It means, if I am drawing the root locus, suppose a locus is found here. If it is moving towards the imaginary axis, then my stability will decrease. If it is moving away from this imaginary axis, this is the imaginary axis, right, then if it is moving away from imaginary axis, then my stability will increase. Okay. So, basically this type of concept we can obtain when we know about the dominant pole. So, what is happening if I shifting my root locus in the left half, it means my closed loop pole are away from the imaginary axis. If my poles are away from imaginary axis, then what would be the response? Then you will find your system would be more stable and the speed of the system would be very high. Okay. So, whenever the pole location is more far away from the imaginary axis, then the speed of the system would be high. So, to understand this concept, we are going for the concept of dominant pole. Okay. So, for this case I will take example of one equation. Suppose this is the transfer function 1 over s plus 1 and s plus 10 is given. Okay. So, this is a transfer function is given here, you can say G s is given here, right, and we would like to see it response in time domain. So, I can further simplify it m 1 upon s plus 1 plus m 2 upon s plus 10 with the help of partial fraction, or after taking the inverse Laplace transform I will get m 1 exponential of minus t and plus it is m 2 exponential of minus 10 t, right. So, if I plot this m 1 exponential minus t, so I will get a graph like this. Okay. So, here you can say it is coming with respect to time and this one we can say m 1 value would be here, and if I am plotting the m 2 exponential of minus 10 t, so this is corresponding to m 1 exponential minus t. So, if I am going for the second term m 2 exponential minus 10 t, it will very fast decays to the value of 0. This is corresponding to e 2 exponential of minus 10 t. It means decaying of second term is very fast. It means it is very fast as compared to the first term, right. So, it means if I combine this response, so it will dominate as compared to this response. So, the impact of s plus 10 would be very less, impact of s plus 1 is very high. In short, we can simplify, if I would like to see the dominant pole which is affecting my system, it is basically the s plus 1, right. So, this is telling us if my pole is very far away from the axis, you can say s equal to minus 10. So, this will gives me very fast response. So, whenever I want very high speed in my system, in the designing of the system, then I need to keep my pole very away from the imaginary axis. So, these poles are known as insignificant pole, and the poles which are closer to imaginary axis, they are known as dominant pole. So, here s plus 1, you can say s equal to minus 1 is known as here dominant pole, because it is affecting my system, right. So, whenever we need to calculate the DC gain, you can say whenever I want to convert the transfer function G s in terms of dominant pole, so we can't directly write this, okay. We can't directly write this expression. So, we have to observe that the DC gain should be same before conversion into dominant pole format. So, whenever we need to write the dominant pole, you can say transfer function. So, I need to calculate the DC gain here. So, here I will write G s equal to 1. So, I need to write this expression in time constant form, that is 1 plus S t form. So, I will write here 1 plus S multiplied by, I will take common 10 here, it is 1 plus S by 10, or I can write here it is 0.1 over 1 plus S multiplied by 1 plus S by 10. Now, my DC gain is coming here 0.1. Okay. So, now we can say here my G s for dominant pole can be given by 0.1 over 1 plus S, and we can neglect this pole because its importance is very insignificant here. Okay. So, basically how to identify a dominant pole. So, basically we need to see there should be a factor of or gap of 5 in between the two pole. If two poles are far away with a gap of 5, then we can say they are belongs to insignificant pole, and the pole which is near to imaginary axis, we can say that will come under concept of dominant pole. Okay. So, this thing we need to keep in mind. Then we would like to see the basic rules for construction of root locus. So, here my starting point is k equal to 0. So, G s h is given as k n s over d s, n s is numerator, d s is denominator part. So, here I need to write quadratic equation 1 plus G s h s for the plot of root locus, okay, because we are plotting the root of quadratic equation. So, this is the basic step. I need to determine quadratic equation from open loop transfer function. Okay. So, it is given as from this expression 1 plus k n s over d s. Now, I need to put it 0 to determine its roots. Okay. After solving, it is coming d s plus k n s equal to 0. So, the root of this equation will give us the closed loop pole, and this is basically a quadratic equation, and its root will be here a closed loop pole. Now, my starting point is k equal to 0. So, whenever I put k equal to 0 here, this term would be 0, I will get only d s. So, here you can find d s is equal to 0. What is d s? D s is the open loop pole, right. And what is d s here? You can say d s is coming in the denominator also here when I solve it. So, this is again a closed loop pole. So, whenever my k is equal to 0, then I can say the closed loop pole is equal to open loop poles. Okay. So, one important condition is coming here, whenever my d s is equal to 0, then closed loop pole is equal to open loop poles. When k equal to 0, then open loop pole become closed loop pole. This is the summary that we had obtained, and root locus representation, you can say what is root locus? It is a representation of closed loop pole, but always start from open loop poles. Okay. So, root locus always start from k equal to 0, it means root locus always start from the open loop poles, right. This is the one information we are getting from the derivation. Now, we would like to see where our root locus will terminate. So, root locus will terminate or ending point is k equal to infinity. Again, I will write this equation from quadratic equation d s equal to plus k n s equal to 0. Now, here I am making k tends to infinity, right. It means my d s is very small, I can neglect d s. So, here my k n s is equal to 0. Okay. So, here when I put k n s equal to 0, so what is n s here? You can see. So, n s in the open loop system, it is giving you the open loop zeros. Okay. So, whenever I am putting k equal to infinity, so here k n s equal to 0, right, and we can say the closed loop pole, we can say at k equal to infinity, the closed loop pole will become here open loop 0. So, whenever I am equating this term, it means our closed loop pole will become here a open loop 0. Okay. So, root locus in summary, if we see, it will start from the open loop pole and it will terminate at open loop 0. Okay. A very important term, that the root locus will start from open loop pole and it will terminate at open loop 0. Okay. In between, whatever value of k will come, it will show us the closed loop poles. Okay. So, if there is no open loop zeros, then root locus will terminate at infinity. So, we will see if in a certain transfer function, if open loop poles are not given, in that case our root locus will terminate at infinity. Okay. So, the remaining session we can say we would like to see the certain rules of root locus in the next lecture. Okay. So, thank you for today. Remaining session we will continue in next.